Greetings, everyone. Please just confirm if I am visible to you, if my screen is shared properly, and if I am audible in the chat box. All right, thank you. So let's get started. I very wholeheartedly welcome you all to today's webinar by the Google Developer Student Club of Rajasthan College of Engineering for Women, Jaipur. And today we are going to talk about machine learning. So we are basically going to discuss about machine learning and the various type of, differentiations within machine learning. And also we're going to talk about the Google's machine learning toolkits and its various functionalities and software it offers to us. So let's get started. So the very first thing I'm going to talk about is the types of machine learning. So we all know what is machine learning. We must have heard about it at least, right? But the point is, we need to get in-depth knowledge about machine learning if we really want to build our career in it. Being developers, we need to know in depth about it because it definitely have a lot of mathematical terminologies. It's amalgamation of mathematics along with coding, specifically Python. So I really want you to at least have a broader idea today about machine learning. What is it? What are the types? What are the advantages, disadvantages, and maybe just a pictorial representation of the different types of machine learning, so that even if you want to learn more about it, you are interested in it, it won't really create any hurdle, right? So when we start about machine learning, as you can see on the slide, so there are basically two types of machine learning. The first one is the supervised machine learning, and the second one is the unsupervised machine learning. So there are again two types. One is discrete and one is continuous. So if we are talking about discrete and supervised learning, then it can be either classification or categorization. As the name suggests, we classify things into different categories. We'll talk about all of them in the further slides. It's just a brief idea I'm trying to give you here. Then the next thing is, if we have discrete and unsupervised learning, in that case, we are talking about clustering. So clustering is basically where we talk about the discrete and unsupervised learning techniques. Then the third one is continuous and supervised learning. There we have regression. And the last one is continuous and unsupervised learning. So there we have dimensionality reduction. So these are the basic types that we have currently in supervised, unsupervised learning in terms of discrete and continuous types of categories. So let's get started with them. So right now, we are firstly going to discuss about clustering techniques. So clustering is again one of the most important techniques. You must have heard about it. And as you can get an idea from the name itself, here we form clusters. We try to form different type of clusters between the similar objects using machine learning, and it is discrete and it is unsupervised. So unsupervised and supervised learning are basically two type of learning, in which unsupervised, we do not have a specific set of outcomes already predetermined, and in supervised learning we have a set of outcomes predetermined, and we just allow the machine to evaluate itself and give its own set of results, and then we match. So in clustering we have discrete outputs. That means we divide the items into discrete categories. Okay, we make clusters of them. So after that, we talk about classification or categorization. So classification or categorization, as the name suggests, is a technique in which we try to classify or we try to categorize things, So again, it is discrete, but it is supervised. So let me give you a better differentiation between the two, supervised and unsupervised. So if we start with supervised learning, so a supervised learning basically uses labeled data, or you can say there is a set of output, and we allow the machine to take the input and predict the output on its own, but we do have a labeled data. Okay, but if we talk about the unsupervised learning, we do not use the labeled data. Therein we just give machine the input, feed it and with the data, and it just gives us the output. So this is the very basic differentiation between the two. After that, we move forward to this. So in this slide, we are going to talk about the machine learning framework. So apply a prediction function to a feature representation of the image to get the desired output. Now, what happens is basically in machine learning, we feed the machine with some data. We give it some sort of input and it is expected to provide us the output, right? So here we have taken an example that say f is a function which is fed with an image. So the machine has to predict what is it. So here if we feed it with an image of apple, it gives us the output apple. So we can assume it to be a machine learning model which is fed with some input data and it just gives us some sort of output. Again, in the next example, we feed it with the image of a tomato and it gives us in result the output, the tomato, okay? Then we feed it with an image of cow and it gives us the output cow. So this is basic functionality of machine learning. In very core concept of machine learning is this, that we feed it with some data and we expect it to give us some sort of output. And output and input are the two main categories, and the data is the integral foundation of machine learning, because no matter if you use supervised learning, if you use unsupervised learning, you are always going to require these three things no matter what. Okay, so yeah, let's move on to the next thing. In this, y is an output. As I discussed before, the prediction function is f and x is the image feature. We are comparing this equation to the previous slide that I've shown, wherein we fed the function f with some sort of image and it predicted the output. So here it has explained what these are exactly. So y is an output. Herein we have used prediction function f and it is fed with some input image feature as x. Okay. So training, what exactly is training? So given a training set of labeled examples, that is x1, y1, x2, y2 till xn, yn, estimate the prediction function f by minimizing the prediction error on the training set. So one of the most integral part of training a machine and feeding it with input and expecting some output is that we want to minimize the error that it creates during the prediction. So that is basically the prediction error. So we feed the machine with some training data because just for newbies or the fresh student in freshman year, I would like to give you a simple example. For example, whenever we have a small child, we tell them about different type of dogs. Whenever we see a dog, we tell them this is a dog, right? So again, dogs are of different breeds, right? So the child in itself just gets an idea of what is a dog, right? So even if it is it encounters any different breed of dog, the child will be able to recognize that it is a dog, right? So here you can assume the machine learning model to be a child, wherein we feed it with some sort of training data. We train it, we give it various type of examples, we try to feed it with various type of data, and then on the basis of that data which we have fed, we want it to produce the output on unseen data. Okay, so this is the very basic example through which you can relate what exactly is machine learning model. And the training data is the data that we feed in the model, and testing data is that data through which we test if the model is predicting things correctly or not. So testing data, as the name suggests, is the unseen data. Okay, testing data, apply f to a never before seen test example x and output the predicted value y is equal to f of x. Exactly what we talked about. We train it with some data. We have some set of examples. X and y here are basically representing x is the input, y is the output. So we have given it a data which has a set of input, output, input 1, output 1, input 2, output 2, and so on. And we have fed that data into the machine. After that, while we are testing the machine, we expect it to generate the output y for a never before seen sort of input data, that is x, and when it is fed in the function f of x. So I really hope that you must have got a clear idea of what exactly we're talking about and how machine learning models can be related to simple mathematical equation y is equal to f of x. So just to give you a better demonstration here, I have chosen this. First of all, we have training. Okay, So in the training data, let us assume all the images that you see here are the training data. So here you can see the first line contains different types of images of apples. Some of them are red, some of them are green, light green. Then next, second line has guavas, different shapes and colors. Then we have tomato, and then we have different animals like in the fourth line we have cows, then we have dogs, then we have it looks like a horse. Yeah. So there are different types of data that have been fed in the machine, and these are known as the training images. What happens after it? The machine basically creates the image features. So what exactly is an image feature? An image feature is basically whenever we feed the machine with some sort of input, it divides that input into features. Now, what is a feature? In a very layman language, I would say a feature is you can say a categorization of that input data. That for example, you can say what is it whenever you feed a machine with an image of human beings and an image of dogs, so it will create different features. A human being does not have a tail, but dogs or any other animal does have a tail. So it's a simple feature through which it can differentiate between the human being and the animals. Okay. So these are the type of features it generates from all these different images, so that it can identify similar type of images when they are fed to the machine through the testing data. So after that, it creates the features, then it goes in the training. Training is basically the main thing we are trying to do here. Then we have the training labels. Label data we have already talked about. The input data which has corresponding outputs, that is the label data. So after that, we have a learned model. So when this whole process of training is done, what we get is a learned model. We have a model that has learned something. Okay. It's very simple to just understand and relate it to a human brain, because machine learning is very much inspired from the human brain's functioning. We also tend to train ourselves whenever, even when we do preparation for a mathematics exams, we tend to train ourselves with the questions that we have, and we just recognize some sort of patterns, and when we encounter a new question of the similar pattern, we are able to solve it in the exam, right? So on the similar grounds, machine learning works. Now let's come to the next test data. In the test data, for example, we are given a test image of an apple. So now the task is to identify what is it. Now what the machine will do, it will again abstract the image features from that test image, and then it will use the learned model that we have, the model that has been trained before, and it will try to match the features extracted from the test image and relate them to the features of the training data and try to predict what exactly is that. And on the basis of those features, it will predict that it is an apple if it is properly trained. So these were the basic things, basic steps that we see in a machine learning model. So now let's talk about the features. What are exactly features? Now, the feature can be a raw pixel. They can be histograms. They can be just descriptors. So let's not go into so much detail about different features, because features can differentiate on the basis of the type of data that we feed. Okay. So just for a very basic example, for example, if you're fed with the very first image that you see of a green field, it will try to extract the raw pixels or the density of pixels, so that because whenever we have a field or a tree, the density will be more in terms of pixels. I hope you're understanding what I'm trying to say. And whenever we feed a test data of similar type, it will be easily able to understand it. We have already well understood this in the previous slide. So after that, we have classifiers, the nearest neighbors. So in the very first slide, we talked about classification, and here we are going to talk about the nearest neighbors. So now, just with respect to the slide that I'm showing you here, please just focus on the data that is shown here. So the blue squares are basically the training examples from class 1. Class 1 could be any type, you can assume it. Just for the sake of example only, let us assume that class 1 is apples, okay? And the circles, red circle represent the training example from class 2. Just for the sake of example, again, let's assume they are oranges, okay? Now we have a test example. This was the training data. This whole thing is training data. Now we give a test example. Now this test example lies somewhere near the class 1. That means it is probably an apple. Okay. So now the task of the machine is to identify what that test example exactly is. So it can easily identify that it is an apple. It belongs to class 1 because it forms cluster. So basically class 1 formed a particular cluster, class 2 formed a particular cluster, and the training data that we fed, it related well to the cluster 1. So hence the machine was easily able to identify to which particular cluster does it belong, or on which, a scale, where does it lie exactly, the test data, and it is nearer to which cluster. Okay. So we can clearly see that the test example is nearer to the training examples of class 1. Hence, we will conclude that it belongs to class 1. Here, f of x is the label of the training example nearest to x. All we need is distance function for our inputs, no training required. What happens here is we will use a distance function. In the nearest neighbor, we use distance function. The test data is basically evaluated on the basis of the distance from the training example of class 1 and 2. Since we can see the nearest neighbors of the test example are belonging to class 1, hence we concluded it belonged to class 1. So this is a simple concept of nearest neighbor, that it works on the basis of the distance, minimum distance. Again, we have classifiers linear. Now find a linear function to separate the classes. Now, you can draw a straight line, that pink line that you can see, because there are two clusters being formed here. One is of the blue squares, another one is of the red circles. And these two can be easily classified in a linear fashion by drawing a simple line in between them. So here we have a very complex kind of formula, I would say. So let's not, focus more on it. The basic goal here in this webinar is just to get the understanding. And just for the knowledge purpose, I have put it there, so you can just note it down if you wish to. But otherwise, the main idea is just to understand what exactly is linear classification. Okay. So now after that, in this slide, we have types of classifiers. So there are different types of classifiers. All of them are given here. First one is SVM. Then we have neural networks. Then we have naive Bayes, Bayesian network, logistic regression, randomized forest, boosted decision trees, K nearest neighbors, RBMs, and so on. So you must have understood, the things that we have discussed till now are very, very abstracted things. Machine learning is very, very deeper than what we have discussed till now. We have just gotten broad idea of what exactly is machine learning, what are the types, it's continuous, it's discrete, it's supervised, unsupervised. And then we have got the idea of classification and categorization and stuff like that. But it has so many other types within it. They have so many, much more other types within them. It's really complex. So you must have your foundations really, really strong if you want to understand these things in detail. And being a developer, I believe we have the advantage to choose whatever field we want to. You can make your mainstream as machine learning engineer. You can become mainstream as a cloud engineer. You have a lot of choices. And I believe just to explore which one do you really want to become, you must know what exactly these fields are, because all of us have heard about them, but most of us don't really have a basic idea what exactly they are. So just for that, I recommend you to please at least have a basic knowledge of every field, and then just try to evaluate your own self in which field you want to go ahead. So now let's talk about this. This is basically the recognition, task, and supervision. How do we recognize? How do we do the supervision? So here you can see in this image, this is a bike, okay? So images in the training set must be annotated with the correct answer that the model is expected to produce. So we have already talked about the label data, that is supervised data, okay? So in supervision or supervised data, we have labeled data. What does that mean? We have labels to the inputs. So training data is a data that the machine is fed with. And in supervised learning, we have input data, and we also have a corresponding output to that data. Okay. So for example, if we feed our machine with this image, we would give it that, we would feed it with this image, and along with that, we will give the output that it is a bike. As simple as that. So here you can see it contains a motorbike. So this is something we have already told our machine. And here in the red box, like, we have shown that how the model is going to recognize that it's a bike or motorbike. So after that, you can just see the process. Machine basically does not care about the background. It works on the bike particularly, because we're not talking about the whole landscape, right? We're just talking about the motorbike. So even if there are trees in the background, even if there is a road in the background, it doesn't matter. We are not talking about them. They're different objects. Machine needs to identify this. Otherwise, whenever it sees a road, it will say it's a motorbike, which is wrong. So here the machine is trying to evaluate which portion belongs to motorbike, what are the features, how does it look like. It has two circular things on the front and the back that are basically tires. So in this way, just in a layman language, we can evaluate that the machine is trying to figure out how does a motorbike look like. Then it has made some, key areas. It has divided it into 5 portions. Okay, now let's talk about generalization. So in case of the generalization, as we can see here, we are given a training set, labels known, and then we have a test set of labels unknown. So this is how we basically feed our machine learning model. How well does the learned model generalize from this data it was trained on to a new test set? Okay, so we are going to talk about it. So components of the generalization error. So again, there can be some errors in generalization. Bias definitely means, now what does bias mean? We can evaluate it from the name, that for example, you fed it with 90% photos that belongs to an apple, right? From different angles, different colors, and just 10% of the photos belongs to maybe guava, okay? So this is a biasing in the data. You have not distributed the data properly. You have biased it. So how much average model overall training set differ from the true model, okay? So we should not do that. We should provide the balanced training set so that the model can easily identify guavas even when it is fed with guavas images as a test set. Error due to inaccurate assumption simplification made by the model. Now what will happen whenever a complex image of a guava comes, it won't be able to identify because it's not trained enough to identify a guava. It was trained enough to identify an apple. As simple as that. Then we have variance, how much models estimated from different training set differ from each other. So this is basically variance. Underfitting of the data. So underfitting is and overfitting is a very general term that we usually use in machine learning models. Underfitting is basically model is too simple to represent all the relevant class characteristics. So overfitting is basically bias, or you can say that it was the data was overfitted, and underfitting on it's basically contrast of overfitting. Underfitting is that the model is overly simplified, it has high bias, it has low variance, it has high training error and high testing error. There are a lot of errors that are occurring here. And overfitting is that the model is overly complex and it fits the irrelevant characteristics, or you can say the noise, that we have to predict apple or guavas and we are feeding it with the test images of maybe a monkey, just for an example. So just kind of that, you can get an idea of what we are talking about. It has low bias and high variance. It has low training error and high testing error. These are the 2 different key points that you must really know and understand the difference between the underfitting model and the overfitting of the model, okay? Now, after this, we talk about the bias variance trade-offs. What does it mean? As you can see in the images, model with too few parameters are inaccurate because of large bias, not enough flexibility. So if they do not have a lot of parameters, they will become inaccurate because they won't be able to identify things properly. Okay, they won't be they will be inaccurate because they will have biasing, a large amount of biasing. They won't be flexible. They won't have variety of training set, but rather the training set will have same type of parameters, hence the variety won't be existing. And models that have too many parameters are also inaccurate because of very high variance. Okay, so too much sensitivity to the sample. All right. Now here we have another formula that we can understand. E of MSE. This is basically noise raised to power 2 plus bias raised to power 2 plus variance. So noise raised to power 2 is basically the unavoidable error that you just cannot avoid, because even in the most perfect model, there is always a chance that there must be some error, some sort of error. Okay, and then we have error due to incorrect assumptions. The error due to incorrect assumption is bias raised to power 2, and then we have variance, error due to variance of training samples. Okay, now this is something that we talk about. Here we talk about this bias variance trade-off. Here we have drawn a simple graph between error and complexity. So if the high bias and low variance, then the error will definitely be very high. But if we have we are talking about training error, to be very particular. If we have low biasing and high variance, then the training error will be less. On the other hand, if we talk about the test error, if we have high bias and low variance, then again, the test error will be particularly high. And in low bias and high variance, it will be comparatively less. Now, here we have marked underfitting. What exactly is underfitting? We already talked about the characteristics of underfitting, that it has high bias and low variance. And overfitting is the point where we have low bias and high variance. So we have got a fair idea of what exactly they are. Now, let us talk about the size, how the training size, have its effects on the model. So here we have a graph where we have error and the number of training examples. Okay, so here we can see this is training data and this is testing data. So if we have training examples in a large quantity, then in that case, the training error will slowly and steadily increase, but the testing error will slowly and steadily decrease. This is what we get from here. And the you can see this, the generalization error is basically the gap between the two, the testing and the training data's error. The gap between the two is known as generalization error. There are basically three types of error in general. The first one is inherent, that is unavoidable, you just can't avoid it. We saw it in the formula before. Then we have bias due to oversimplifications and variance due to inability to perfectly estimate the parameters from the limited data. So these are few basic examples that we have here. We easily get the idea of how the training errors, testing errors, generalization errors work out, and how does the size of the training data set affect it. After that, we have very briefly tour of some classifiers. We have already talked about them before: the k nearest neighbors, SVM, boosted decision trees, neural networks, naive Bayes, Bayesian network, logistic regression, randomized forest, and so on. Now let's talk about generative versus discriminative classifiers. So there are two types of models. Okay, first is generative model. The second one is discriminative model. So in generative model, what happens is it represents both the data and the labels. So whenever we have data and we have labels as well, that is basically the generative model. On the other hand, the discriminative models, they learn to directly predict the labels from the data. Here you must be getting a vibe of unsupervised and supervised learning. Okay, so the generative models are those that often make use of conditional independence and priors, and discriminative models often assume a simple boundary, or you can say linear boundary, as we have done before in one of the slides, where we simply draw a line between the two different clusters of training set. In generative models, we have the example of naive Bayes classifier, Bayesian network, and in discriminative models, we have example of logistic regression, SVMs, boosted decision trees. After that, we have generative models. In these type of models of data may apply to future prediction problems, whereas in discriminative ones, it is often easier to predict a label from the data than to model the whole data. So we have got a fairly good idea of what these two type of classifiers are: generative classifiers and discriminative classifiers. We have got difference between the two, and definitely we have got to know the type of examples here, that SPM, logistic regression, boosted decision trees, these belong to discriminative models, and naive-based Bayesian network, these belong to generative models. So let's move on. Classification. Great. So what exactly is classification? Now here you can see in this graph, it's very clearly mentioned. We have classified the whole data in three categories, R1, R2, and R3. So we assign some input vector to one of the two or more classes. So we have basically classified them. We have divided them into classes, okay? Any decision rule divides the input space into decision regions separated by decision boundaries. So the red line you see on the graph is a decision boundary. It's basically the basis on which basically it's kind of a condition or maybe a kind of a parameter on the basis of which we have divided these classes. R1, R2, R3 are the three different type of classes, and these divisions have been made on the basis of the decision boundaries, and these are basically divided into decision spaces. Okay, so this is the basic, very basic core idea of classification. Then we talk about nearest neighbor classifier. What exactly is a nearest neighbor classifier? So as you can see in the data, it's a really complex image, right? So we assign the label of nearest training data point to each test data point. You can see here different type of points. So it is a positioning of the feature space for two categories, 2D and 3D data. So you can just get a fairly rough idea. You need not get in too much depth of this, but just for the fair reference of idea, we have also divided here into the nearest neighbor thing. This is basically 3D space. So there are different type of examples where we use the 3D space, or you can say the 3D images or 3D data, and we try to classify things on the basis of them. So how do we actually differentiate between the 3D objects, or you can say when we club machine learning with AI or VR and so on? So in those cases, basically we use the nearest neighbor classifier, as you can see here, and the red dots belong to one cluster and the black dots form the other one, and so on. All right. After this, we have the K nearest neighbor. So as you can see in this image, there are green circles and there are red crosses, right? And there is a graph x1, x2. And here we are basically trying to figure out the K nearest neighbors. So let's see how it goes. Okay. Now, one nearest neighbor is the first thing that we're going to talk about. One nearest neighbor is simply when we find the one neighbor that is nearest. For example, we have those black plus signs here, and we found the nearest neighbor, one nearest neighbor to these black signs, black plus signs. Okay, it represents that the one of them is nearest to the red colored X, and one of them is nearest to the green colored circle. So we have just found one nearest neighbor to both of them. Now, what if we need three nearest neighbors? You can see here. In these two different green circles, we have found three nearest neighbors to that one black plus sign. Okay, so the first one has one red cross sign and the two circles in green, and the other one also have the same, but there are three in total, right? So this is three nearest neighbor. Again, the same scenario, five nearest neighbor. We have five nearest neighbor for one black colored plus sign. So this is a very basic idea, very abstracted idea of how exactly the nearest neighbor thing works for one nearest neighbor, two nearest neighbor, three nearest neighbor, five nearest neighbor. Now let's talk about the advantages of ML. What exactly ML have in store for all of us? I believe that ML is a booming field of technology in today's time. We definitely have a lot of scope in here, and machine learning in itself is requiring a lot of talented professionals. We need to have in-depth knowledge in order to excel in this career. And definitely just to gain the knowledge, we need to have strong basic foundations. And that is the reason we are having this webinar today. So especially for the people in freshman year, I recommend you all to just know at least the basics of each and every field, and then try to explore the one that suits you and interests you the best. Okay. So firstly, let's talk about the advantages of machine learning. The first advantage is that it identifies the trends and the patterns very easily. we have already seen that there were different kind of trends, there were different kind of patterns, and they were identified. For example, we had images of apples and guavas. It definitely found out the patterns, right? That apples are usually red in color, guavas are usually green in color, and it easily predicted. Okay, so it very easily finds the trends and patterns. The next one, it improves itself over the time. So when we feed more data, it just helps to improve the machine learning model, because the more the data we feed, the better it will result, but not always. Definitely we have the cases of overfitting and underfitting of data. But still, if we are being very, very careful in terms of these two terms, and then we feed data, it will definitely improve over the time. Okay, it will understand the patterns better. Then it is self-sufficient and assorted. Again, machine learning is definitely self-sufficient. We have a lot of examples of machine learning around us today. For example, we have automated, even machine learning is nowadays used for those automatic cars. You can say we have Tesla and so on. What does they work on? Computer vision? What is it exactly? It specifies the objects. It basically differentiate between the objects and humans, and then it just automatically works. Automatically, it is driven by itself. The machinery drives the car itself, and the user doesn't even have to do anything. So these examples are basically the future of mankind. Machine learning holds the future of mankind. And I particularly believe that in the coming decades, in fact, this is a reality, we all know this, in the coming decades, there is going to be even more development in this field, and we might even see robots in our households in India. So we should know about this field, I guess, being developers. It definitely saves a lot of time and energy efficient. So machine learning is definitely energy efficient. And as I told you, if you have an automatic car, you don't have to drive. As simple as that. So whenever we are using machine learning for our day-to-day tasks, we are automating the things. We are making our lives easier, eradicating the real-world problems. So yes, it's really great. Now, every coin has two sides. It has pros, it has cons. So now let's talk about the disadvantages. So the very first disadvantage here is that the errors are frequent and they take a long time. So if you have some sort of error in your machine learning model, then it is definitely going to take some time to figure it out, because we have already talked about generalization error, training and testing errors, overfitting, underfitting. A lot of things are, types of error can happen, and machine learning models are very sensitive to these errors, So these errors are frequent and they happen, frequently. And moreover, sometimes if the error is like really big, it can actually take a lot of time to improve. And this can actually do disasters, because we use machine learning in our day-to-day life. So it is expensive. Definitely machine learning requires a lot of training, a lot of testing, and then even the softwares or even the equipments that use machine learning, whenever they're launched for public use, they are tested a lot of times. A lot of time is being spent in testing and training them so that they don't do accidental mistakes when they're used by the common public, right? So definitely they're meant to be expensive because they take a lot of effort to develop, okay? So they have to be specialized for each and every project. If you're working for, say, in a very layman example, if we are training a machine learning model for apples and oranges, we have that specific data to be fed in it. Now, on the other hand, if we are training it to recognize the objects or maybe a motorbike, as we saw, then it has to be trained with different algorithm, with different training and testing data set, right? So according to the project, according to our task, the training, testing data, and the type of algorithm we use, all of these things change. This is a very, very vast, dynamic, and complex field. So yeah. Now let's talk about the Google machine learning project products and the machine learning kit. I must say that Google is really doing great job in terms of developing the softwares based on machine learning and AI. And most of the Google products, like voice assistant we have in our Android phones, for example, all of them are based on machine learning and AI. Okay, so Here I have shown you the image. You can also search it on the Google search, that ML kit. What is it exactly? So basically, it basically has, as you can see on the screen, barcode scanning, face detection, image labeling. These are the different kind of APIs. Okay, so it has some sort of APIs that you can use, and you can also use them to develop your own models, your own softwares, and so on. And at the same time, there are a lot of different applications which are specific to machine learning. For example, if we talk about TensorFlow, it is an open source application and it is specifically for machine learning. So there are a lot of things that are given to us by Google for particular use, and we are very grateful that they're open source. So yeah, you can have a look at them, you can explore them. And I think this is the end of the session. Thank you so much for joining. And I really hope that you must have got a fair idea of machine learning, its types, its examples that we have talked about so far. We didn't cover each and every algorithm because these are really complex. I have just tried to give you a fair, broad idea in a very abstracted manner, so that at least you have, some knowledge about each and everything. Now, whatever interests you to start with first, you can go with that. And now you know what is supervised learning, what is unsupervised learning, continuous, discrete, different type of noises, underfitting, overfitting. These are the very basic terms. So I really hope that you benefited from this webinar, you learned something, and that you will use this knowledge to further implement, innovate different type of softwares, and eradicate the real world problems. And yeah, that's it. Thank you so much for joining this webinar. I really hope that you have a great day ahead. Thank you.